Hello, I am Mr. S.S. Sazne and I am teaching the subject thermal engineering. So we have already started with our first chapter, that is fundamentals of thermodynamics, and today we will start with a new point. But before going or heading with the new point, we will just have a flashback of our previous lecture in which we have studied several important points from this chapter. In the previous lecture, we have started with the second law of thermodynamics. So in that we have already seen the two statements for the second law, that is nothing but Kelvin Planck statement and Clausius statement. So first, if we see what is Kelvin Planck statement, then you should remember what statement I have already given you. So it states that it is impossible to construct a device working on a cycle that would convert the entire supplied heat energy into equivalent amount of output work. So in short, you can just remember that whatever the heat energy is supplied to the device or machine, that machine will convert entirely the input heat energy into equivalent amount of work. So this such kind of machine is not possible to construct. So this was the Kelvin Planck statement. Again, we have seen Clausius statement, and in that Clausius statement, the statement was as follows: it is impossible to construct a device that operates in a cycle which extracts heat from a low temperature reservoir and supplies it to high temperature reservoir without any external energy. So again, simply we can understand this statement as we can never construct a machine or device that would transfer the heat from low temperature reservoir to high temperature reservoir unless we are giving some external energy to it. So these were the statements for Kelvin Planck and Clausius statement, which will cover the second law of thermodynamics. So we have also seen the examples for both these statements. Then after this second law of thermodynamics, we have seen what is perpetual motion machine of second kind. So a lecture previous to that, we have also seen what is PMM1. So you should understand the difference between these two types of PMM, that is perpetual motion machine of first kind and perpetual motion machine of second kind. So in previous lecture we have seen PMM2. In that we have seen that the machine which violates the second law of thermodynamics is nothing but perpetual motion machine of second kind. So this machine it has actually 100% efficiency, that is whatever input is given to that, the machine will entirely convert that input into equivalent amount of output. So this practically is not possible, and so we call it as a perpetual motion machine of second kind. So practically such machines are not possible to construct. So after PMM2, we have also seen, or we have concluded our previous lecture with a reversible and irreversible process. So I think you might remember what I have taught in that previous lecture. So the reversible process are the process in which the system and the surrounding can be restored to the initial state from the final state without producing any changes in the thermodynamic properties of the universe. Whereas the irreversible process is the process which we cannot return both the system and surroundings to their original conditions. So for the same, I have also given the example of spring for in case of reversible process, whereas in case of irreversible process, I think I have given the example of tea. So whatever the ingredients we are mixing and heating up to prepare tea, so if we want to bring back again the constituents or ingredients from that tea, then it is never possible. So with these examples, you might also have understood the concept of a reversible and irreversible process. So today we are going to continue with a new point which is related with this second law of thermodynamics, and it is nothing but equivalence of Kelvin Planck and Clausius statement. So theoretically, if we see, this point is or the theory part for this question is very much lengthier, but if you understand with the help of diagram, then it will become very much easy. So in this equivalence, what we are going to study is we are just going to relate both these statements we actually are studying these two statements differently, that is Kelvin Planck for heat engine and Clausius statement for heat pump or refrigerator. But if we study the second law of thermodynamics, then since both these statements are included under second law of thermodynamics, we can assume both are equivalent. So to prove this, we are just going to assume, or we are going to consider two cases. In the first case, we are going to violate the Kelvin Planck statement, and we will see what will happen to the Clausius statement. And in second case, we are going to violate Clausius statement, and we will see what it causes the effect on the Kelvin Planck statement. So in further slides, we will see both the cases. In this slide, we are going to study the equivalence of Kelvin Planck statement, and the first case for the same, that is we are going to violate the Kelvin Planck statement, and we will see what it causes the effect on Clausius statement. So first, I think you should understand the meaning of this word violation. So violation means thinking exactly opposite. So we have already studied the Kelvin Planck statement, that it is impossible to construct a device which will convert the entire input heat energy into equivalent amount of output work. So we are going to do exactly opposite this statement, and it is nothing but violation of Kelvin Planck statement. So we can see here we are having two diagrams, but initially you should just focus on the first diagram. So before starting with the actual explanation, I would first like to introduce what are the terms involved in this diagram. So we are having high temperature reservoir, which is indicated by the red color. At the bottom, we are having a low temperature reservoir, which is indicated by blue color. So the temperatures for both these reservoirs are represented as TH for a high temperature reservoir, and TL for the low temperature reservoir. Again, in between these two reservoirs, we are having two devices or machines which are nothing but a heat engine and a refrigerator. So we are considering these two devices, that is we are taking the combination of Kelvin Planck statement and Clausius statement, because we know that Kelvin Planck statement is for heat engine, whereas refrigerator or heat pump is for Clausius statement. So we are going to take combination of both the systems, and we are going to violate the Kelvin Planck statement, and we will see what happens to the Clausius statement. So in the first diagram, we can see that the Kelvin Planck statement is violated, that is heat energy is taken from the high temperature reservoir, which is represented by QH. This heat is nothing but the input to that machine, that is heat engine, and this heat engine is converting this entire input heat energy into equivalent amount of output work. So the output work is represented by capital W, which is shown as W net in the diagram, and this work is nothing but it is equivalent to heat energy, that is QH. So here from diagram you can understand that the entire input heat energy to the heat engine is converted into equivalent amount of output work. So we can write that W is equal to QH. So this machine is having 100% efficiency, which is practically not possible. So now again, if we see the other part of the same diagram, that is if we focus on the refrigerator or heat pump, then whatever the work we are obtaining from the heat engine, the same input work is provided to the refrigerator or heat pump. So we can understand that what we have studied in Clausius statement, that we cannot transfer heat from low temperature reservoir to high temperature reservoir unless we are providing some external work. So here in this diagram, the Clausius statement is not violated, because we can see that the heat is transferred from low temperature to high temperature reservoir. However, we are also providing some external energy which is coming from the heat engine. So here only Kelvin Planck statement is violated. However, the Clausius statement is not violated. Now we will see what happens if we combine both these systems together. So we are going to take the resultant of both this system, that is heat engine and refrigerator, and whatever the resultant is coming, we have shown that in the other diagram. So you can see that diagram on this right side. So to understand how this resultant diagram comes, you should first understand what actually sign conventions we are going to take. So when we are taking the combination of both the systems, or resultant of heat engine and refrigerator, so in that case, whatever the arrows that are shown in upward direction, we will consider that as positive, whereas the arrows that are shown in downward direction, we will consider that to be negative. So opposite arrows with opposite signs. I will repeat again, you should understand these sign conventions very properly, or else you will not understand how this resultant or the equivalent diagram has came. I said that whatever the arrows that are shown in upward direction, we are going to consider it as positive, whereas the arrows that are shown in downward direction, we will consider those as negative. So if we combine both these systems or machines, that is heat engine and refrigerator, then what will happen if we apply these sign conventions? Now, if we focus on the arrows which are in between the two given devices, that it's heat engine and refrigerator, and low temperature reservoir. So in between these two parts, there is only one arrow which is in between a refrigerator and low temperature reservoir, and it is represented by QL. Since it is in upward direction, we will consider it as positive. Since there is no any arrow on the heat engine side, so there is no any problem. So now if we consider the arrows which are in between the high temperature reservoir and in between heat engine and refrigerator, so here we can see that there are two vertical arrows and one horizontal arrow. So first we will consider only about the vertical arrows. So the in between high temperature reservoir and refrigerator, there is one upward arrow which is the summation of QH and QL, whereas there is one arrow in between high temperature reservoir and heat engine which is represented by QH, but it is coming in downward direction. So when we are combining both these systems, then we will consider QH plus QL as positive, and we will subtract QH from this. So the resultant that we will get is nothing but QL. Okay. Now someone of you will ask that what we are going to do about that horizontal arrow. So if we are going to combine these two devices, that is heat engine and refrigerator, then clearly you can see that one QH is going in upward direction, whereas one QH is coming in downward direction. As a result of which these opposite directions, the QH will be totally eliminated from the system. And if there is no any QH going to the heat engine, then there will be no any work output. If you are not going to give any input to the engine, then it will never give you output. So as a result, the W, that is nothing but work, it will be also get cancelled. And as a result, we will get the equivalent diagram after combining this system, which is shown on this right side. So here, by observing this diagram, you can clearly understood that the Clausius statement is also violated. Okay, this is because the heat is transferring from low temperature reservoir to high temperature reservoir without consuming any external energy, because the work has been cancelled while we are combining both the systems. So from this we can understand that if we are violating the Kelvin-Planck statement, there will be also violation of Clausius statement, and this concept is called as equivalence of Kelvin-Planck and Clausius statement. This shows that there is a relation between this Kelvin-Planck and Clausius statement, or in other words, we can say that Kelvin-Planck statement and Clausius statement are not different, they are actually the same. We will also understand, or we will see the reverse case for this equivalence. That is, we will also see what will happen if we are going to violate the Clausius statement and what will happen. So we will see this concept in the next slide. Now, as said in the previous slide, in this slide we will violate the Clausius statement, and we will see what happens to the Kelvin-Planck statement. So for this purpose, we will again consider a combination of the two devices, that is a refrigerator and heat engine. So again we will understand first the diagram. We are having two reservoirs, that is a low temperature reservoir which is at temperature TL, and a high temperature reservoir which is at temperature TH. In between these two reservoirs we are having two devices, that is a refrigerator and heat engine. So now in this diagram we will violate first the Clausius statement. So in the first part of this diagram, that is if we see it on the refrigerator, then there is a transfer of heat from low temperature reservoir to high temperature reservoir without providing any external energy. So thus Clausius statement is violated. On the other hand, if we see on the heat engine side, then there we can see that the Kelvin-Planck statement in this diagram is not violated, as we can see that the input energy is QH. The engine is partially converting this heat energy into some work which is represented by W net, and some amount of heat is also rejected to the low temperature reservoir. So we can say that in this diagram the Clausius statement is only violated, and the Kelvin-Planck statement is not violated. Now if we take the combination of these two systems, just like in the previous slide we have taken the combination, here also we will do the same. So after taking the combination of both the systems, we will apply the sign conventions. So for simplicity, in this case we will consider that whatever the arrows, vertical arrows which are in upward direction, we will consider those as negative, whereas the arrows that are coming in downward direction, we will consider those as positive. There is one more thing that you should be clear about, that is there is no any problem while considering the sign conventions, because in previous slide we have seen that the arrows which are in upward direction we have taken it as positive, and the arrows coming in downward direction we are taking it as negative, and in this slide we are taking upward arrows as negative and downward arrows as positive. So you can take the sign conventions in any way. Just the thing is that the arrows which are having same quantities but in opposite direction, they will cancel each other. So whatever the sign conventions you are taking, depending on those taken sign conventions, there may be possibility that you might require one more additional step for rearranging those factors. So you can take sign conventions in any way. Just remember that whatever the sign conventions have taken for particular direction, there should be exactly opposite sign conventions for that reverse direction. So this was about the sign conventions. So we will now return to our first diagram. If we see the bottom part, that is the arrows that are marked in between refrigerator, heat engine and the low temperature reservoir, then we can see that there are two arrows which are in opposite direction, and both are nothing but QL. As a result of this, both will cancel each other since they are both in opposite direction. If we speak about the arrows which are present in the upper part of the first diagram, that is refrigerator, heat engine and high temperature reservoir, then in between these we can again see that there are two arrows, but both are different. In between refrigerator and high temperature reservoir there is QL, whereas in between heat engine and high temperature reservoir there is QH amount of heat. So while combining both these systems, we will consider it as QH minus QL, because QH is nothing but the heat coming from high temperature reservoir. So it will be always maximum, whereas QL is the heat coming from low temperature reservoir. So it will be always minimum. As a result of this, we will be taking that value as QH minus QL. So the resultant diagram that we will be obtaining is shown in the right hand side. So we can see that there is addition of heat to the device, which is QH minus QL, and the device is converting this input heat energy into equivalent amount of output work. However, there is no any heat energy lost to the or rejected to the lower temperature reservoir. So from this we can say that the Kelvin-Planck statement is also violated. So from this slide we will understand that if we are going to violate the Clausius statement, there will be also violation of Kelvin-Planck statement. So I hope that you might have now understood what is the concept of this equivalence of Kelvin-Planck as well as Clausius statement. With the concept of equivalence of Kelvin-Planck and Clausius statement, we will stop here today. Almost all the points from this chapter has been covered. There is only one more point remaining, and that is a steady flow energy equation. You have to study what is the meaning of steady flow energy equation, and also derive the equation for several devices such as boiler, turbine, compressor, condenser, etc. And this last point will be taken by my colleague, that is Mr. V.C. Gadge. So he will be teaching you this last point from this chapter, and I think that he will require 2 more lectures so that this chapter will be completed. Very soon I will also share the notes for this chapter so that you can study for the exams as well. So we'll stop here now. Thank you.